All right, well, I'm not sure if we can get started at this point, so we'll give it another minute and get into it. What we'll be doing today is continuing the assembly of the air engine. So if you haven't already, between last week and this week, please make sure you've downloaded all of the files from Google here, because we will definitely be using them today. Okay. If you just joined, welcome to the class. We're still waiting on a few students. And let me know if you have any difficulties with my audio or video or the screen share, as usual. What you hopefully have from last week is all 6 of these parts inserted into your assembly, and then the first 3 mates. So we fastened the base plate to the assembly origin. We fastened the upright to the base plate. We created a revolve between the cylinder and the upright, and we created a slider between this piston and the cylinder. So if you're not at this point, or if you have any questions, feel free to ask. I see we have another student who's joined us, brings us up to 3. Pretty good start. To give a little preview, today we'll be talking about 3D printing. So as a bit of a disclaimer, I'm not much of an expert in 3D printing, but I'll try my best to tell you what I do know and what is in these slides, which were created by my co-instructor, who is not teaching this class. All right, so I'll start out by talking about 3D printing then. We're a few minutes past, so at this point, people can watch the recording. So as we talked about last week, we drew a distinction between what I called conventional manufacturing or subtractive manufacturing, as opposed to additive manufacturing techniques. And just like for conventional manufacturing, or just like for conventional manufacturing, there's a lot of different techniques. And like for subtractive manufacturing, there's a bunch of different machines that you can use that would fall under this term. For example, we talked about the milling machine and the lathe, which are 2 kind of classical machines that are used for developing parts for prototyping. And likewise, for additive manufacturing, you'll find that there's a number of different devices or machines which can be used to create parts that fall under this kind of philosophy. And so as I said last week, the idea is that we're creating a part by applying material layer by layer in an additive fashion. So we're building things up with some material that's either usually in like a spool form, so it's extruded out from a nozzle, and we're creating things that way rather than starting with a large chunk of our raw material and then cutting it away to reach our final geometry. So when it comes to specifically 3D printing, there are several factors that you should consider in order to successfully create your part, because no matter how good your printer is, if you just run it, it's not going to be an exact, perfect geometric model of the thing that you have in your computer, because a thing like that cannot actually exist, right? We don't have perfectly smooth planes in real life. We don't have perfectly straight lines. Everything will have a bit of a tolerance. So when it comes to 3D printing, especially for kind of a hobby purpose, we often care about aesthetics, but this is also kind of a functional feature as well. So when you talk about aesthetics, that's kind of what the things that you can see, like the surface finish, the outermost layer, and you generally want that to be kind of a smooth and continuous surface. without a lot of imperfections on it. And so some ways you can do that is to reduce the amount of support material you use. Like when you're printing, if you have an overhang, a lot of the time you need to print some support material underneath. And so in order to, whenever you break that off, you'll leave some marks or some protrusions on the surface. And so by removing the support material, you can help to mitigate that. Another way is to minimize the effect of the layers that are visible. And so that's sometimes a part of the 3D printer nozzle itself. If the 3D printer is able to extrude like thinner lines, maybe then it can be, it's a lot cleaner in the final part where you can't see all of the layers. Or at least if the layers are very well bonded together, then you won't be able to see the layers. And in addition to that, in addition to like the surface finish, we also care about kind of the mechanical elements. So even if you have a bad surface after you print something, you can usually make it a bit better just by applying some kind of post-processing, whether it's cleaning in some kind of solution or sanding it by hand. When it comes to the material properties though, we want to make sure that the things that we print are strong, and we also want to make sure that we successfully print our thing. So we want to avoid what's called failed prints. If you're ever curious about what that refers to, you can look up like failed 3D print, and you can see all of these examples of something that went wrong during the 3D printing process, and the result is not exactly what was intended by the designer. So the first thing I'll talk about is first layer adhesion. So often one of the most important layers, the entire process of building the part is in layers where you sequentially apply layer by layer of the printing material. But the first one is very important because you want that'll be one of your like surfaces on the final part. And so for this, you want to make sure that the printing bed is level. And you want to make sure that you orient your part in such a way that you have a large flat surface, if applicable, that is resting on this bed. Another thing that you can do is you can print something called a raft. So in this image, this thing on the bottom is what's called a raft, and then you print on top of that. And that can just help you with your adhesion because you already have another printed layer underneath. Next, we have minimizing the total height of your build. So when we have our coordinate system, just like in Onshape, we have, whenever we describe a three-dimensional space, we talk about our left, right, and top. So in Cartesian coordinates, that's the X, Y, and Z. And so in general, not just for 3D printers, but for most machines, we refer to the Z direction as like the up and down. So a milling machine that's vertical, that also the Z direction would be up and down. Although some machines, they have a spindle that kind of lays horizontal, and in that case, the Z axis can also be a horizontal one. But for 3D printing, usually we refer to Z as up and down, and then X and Y are creating the horizontal plane. So usually X is left and right, Y is in and out, and Z is up and down. So it's important to minimize this Z height because printers move faster in X and Y than they do in Z. And what that means is that if you orient your part in such a way that a lot of the movement that the printer has to do is in X and Y, then the print will finish faster, which is usually good. So you don't always have to put your part in the same orientation that it will be used in. You often want to change the orientation just so that it prints faster and stronger, which is something we'll talk about. And so here we get to surface finish. This is something I talked about a bit earlier. Since 3D printing is done layer by layer, and we're going up and up and up in Z, so we put down an entire layer, then we go up in Z, put down another layer. This means that you're going to have a bunch of visible layers. So if you look up something like a 3D printed surface, what you'll find almost always is that you have a bit of texture here. So you can see like these lines, and those are kind of the marks where the material was laid down with the extruder. Depending on the material and the application, sometimes like we can call them weld marks. Like if you're doing metal 3D printing, you'll see these lines that kind of represent it's a result of the process that created that surface. So that's not always desirable. A lot of the times you design something that's nominally a flat surface, but it's not going to come out as a flat surface just because of the way that this process creates parts. So in general, your XY plane has more precision and you're going to get a smoother surface. Next, we have a discussion on support material. So as you might imagine, if we're printing layer by layer by layer, if you're trying to print a layer and there's nothing underneath it, then theoretically you can't do that because there's nothing for that freshly extruded material to lie on top of. You need to have something underneath. And that's what we call support material. So when you're printing something, you might have to print parts or geometry that's not part of your actual desired final part. As a rule of thumb, if you have an angle that's greater than 45 degrees, so you can see in this picture here, something like this, where you have a very steep overhang. In that case, you should add some support so that the geometry will be closer to the nominal one than it would be if you did not add that support material, because you can imagine that as you go farther and farther out, there's a greater tendency for the printed material to sag under its own weight. And like I said before, if you have the support material, one downside is that once you remove it, you're going to have some kind of mark where that was used to be connected to the part. And then mechanical performance. This refers to kind of the effective material strength of this part that you created. A lot of the time, for example, like for many hobby purposes, it's going to be fine, but if you're designing a part for some kind of more complex system, maybe it's for a robot team, a lot of your parts are going to need to have some structural integrity. They're going to be able to withstand certain loads. And so you need to consider that when you make your print. One common type of failure is layer separation. So when you have a 3D printed part, the layers all kind of lie on top of each other, and you can imagine that what's holding them together, if you apply kind of a shearing force, so you take the top and you push it sideways, when you have that kind of shear, the final part is held together more by kind of where you have the adhesion between the layers than so much a solid piece of isotropic perfect material. So that's something to consider. Again, different orientations are important. For example, if you're creating something like a long rod that needs to support something in tension, for example, you're going to hang a weight off of a 3D printed rod. In that case, you should print such that the layers are printed with a long way in X and Y, rather than printing a large number of circles on top of each other, just because when you're pulling things apart, you want to be pulling effectively these long extruded pieces of plastic rather than pulling apart the layers from each other. So with all that said, the main things to take away is that 3D printing, although it's very powerful technique, it takes away a lot of the work that you personally have to do. You don't have to sit there and manually move the nozzle around, like the machine does the work for you. But even so, there's a lot that you need to consider in terms of taking a CAD model and creating a real part. A lot of the times you need to consider like how important your surface finish is, how important the strength of the part is, and that can guide your decision of what printer to use, what material you need to use, and how you're going to orient your part to prepare it for 3D printing. The slides are posted on Google Classroom, so if you're curious, you can take a look at this link here. I wonder if it works. Yeah, so here, this website provides a guide for you if you are getting into 3D printing and want more information about what you should do. There's plenty of things like this out there, a lot of resources on the internet, including videos. So if this is something you want to do, there's a lot of ways that you can learn about it. So at this point, before I introduce project 3, I want you to open up your Onshape and we'll resume where we left off in assembling this air engine. So I'll give you a second to do that. If you have any questions about how far we got last time, or if you want me to repeat any of the steps that we went over last week, then please let me know. As a reminder, again.
I didn't do this. Can you send me a copy of this? Because I didn't really do this one.
Yeah, so it's not much, we haven't really done that much yet. Just make sure you've downloaded all of these from Google Classroom and you should be fine.
No, like I forgot, I wasn't here. So can you show me again?
Well, you were here last week and that's when we downloaded all the parts. So I can walk you through.
Can you like show me again?
Yeah, I can walk you through I can walk you through the mates again, and that's totally fine. As long as you have the parts in your assembly, then we're good.
Okay, I'm gonna go there and download the file. Can you show me everything? Because I didn't do most of the parts yet.
Right, so like I said, even if you have not done the parts, they're all posted on here on Google Classroom.
Can you show me like after class maybe? Because I can't get to Google Classroom for some reason.
If you cannot use Google Classroom, you should.
No, I can't log in because of my school account.
Okay.
Can you show me like after class maybe?
I don't think I can help you with the Google Classroom part. And
no, I mean, can you show me how to make it after class?
Okay, so I don't think I'll be able to stay very long after class today, as I'm a bit busy. So just keep in mind that all of these classes are being recorded and they go somewhere. So you can ask Miss He about where to find these things, and also about the Google Classroom if you're having an issue with that. For the time being, I will go over the assembly up to now, just so that all of that exists in one place, in one class. The release hasn't been that much so far. We started with a fasten mate to position our parts with respect to the coordinate systems of the assembly itself. So since most of you probably have seen this, I'll kind of go through it quickly, but if you have a question, you can stop me and ask. All right. So this is where we were. I don't think anyone asked me any questions, so I'll assume that you're fine up to here. So from here, we just have 2 parts remaining, and we will have finished this assembly. And so again, for this project, we have a reference of what this thing should look like on the original website. This is kind of what the final product is going to appear as. So next thing I'll do is the crank wheel. That's this one right here. It attaches to the piston as well as the upright. And you can see that in the final crank wheel, we have this hole here, and it will end up aligning with this hole here. So again, here we apply our revolute mate. And the first step that I'll take is to put the crank wheel up against the upright so that it can spin freely there. But you'll notice that it's not yet connected to the rest of what's happening here. So first step, just make a revolute mate for this. And then the next step is where things might get a bit tricky, because you're going to be interfacing 2 parts like this. Okay. So we'll try it. And here there's a bit of a question about which mate that we might try to use. When you think about what kind of behavior you want this to have, if you think about how this assembly will work with these 2 things moving together and following each other, they will actually rotate with respect to each other. So we know we probably want something like a revolute mate or a cylindrical mate. In this case, I think we'll choose a cylindrical mate just because we don't know the exact distance between some part of this hole. So like probably where the mate connector would end up is probably maybe like the center of this hole and some part of this hole. And we don't know the actual like the distances there. So I'll start out by attempting with the cylindrical mate, and we'll see if that works. Create our mate connectors. Just click on the cylindrical bores. Doesn't matter too much which ones you use. And since they're cylindrical, this one, remember, has the freedom to rotate with respect to each other as well as to move axially. And hopefully, if I just solve this and accept it, then they're mated together. And what we'll have here is now you can see that the piston will follow the crank wheel, and we have kind of a reciprocating motion of the piston while the crank wheel is rotating. And likewise, the cylinder is rocking back and forth. So that's a bit of a tricky thing to do, but hopefully if you're careful, you should be able to create your cylindrical mate. If you have any questions about that, feel free. All right, and so the last part we need to add is our flywheel. So here in this case, the flywheel is free to revolve on the upright. In real life, there'd be some kind of shaft and bearing. I think actually for this part, it's just, there might be a shaft, might just be a bolt, but what we will do is place the flywheel on the upright with the revolve mate. And actually, I did this one backwards. If you look closely on the flywheel, you'll notice that one of the parts is farther out than the other. So if you look at it straight from the side, this one has a small boss that protrudes. So that's actually the side that you want to touch the upright. So I placed mine backwards, but now I'll fix it. Get my mate connectors. Like such. And there we go. Now that small boss acts as a spacer between the flywheel and the upright. So now I can freely turn the flywheel, but you'll notice that these two things are not interconnected. The motion of the crank wheel and the motion of the flywheel are not coupled in any way. And there's a few ways, ideally, or like, I just want them to be coupled so that they rotate together, because in real life, the objective of the flywheel is to store energy. And so in order to achieve that, there's a couple ways I believe I can do it. I think one way is using this tool called group. So if I do something like that, you can see now that the flywheel and the crank wheel rotate together. I believe also that you can do it using this gear relation mate. So two ways that you can go about this. I believe with the gear mate of 1-to-1, you can also make them rotate together as such. So two ways that you can go about that. One is this gear relation. The other one is using the group tool here in assemblies. For clarity, you can see here how this moves. And so that is the completed assembly. I did go through that rather quickly, which I now realize, but if you have any questions about any part of putting this together, you can ask me and I'll go through it again. You can also play it as animation. All right, so was everyone successfully able to complete this one? Seems like it seems pretty quiet, so if you were, congratulations. Hopefully it was straightforward enough. And in the event that you cannot follow along for technical reasons, if you have some problem with like the classroom or Onshape or whatever, hopefully there's everything that you need to know was shown. So I believe that you should be able to do it, since the step files are all posted, as well as this was just demonstrated. Okay. So from here, there's a few things that you can think about or try to do. The first of these would be including the fasteners. So if you go to the drawings, which are also posted here, you can see that in this bill of materials that it specifies, I believe, all of the hardware that you need. So for example, a 632 steel machine screw nut, set screws, cap screws, all of this hardware, like washers, fittings, all of this hardware is something that if you were to make this in real life, that you would put in the model, just so you can demonstrate the full assembly with all the hardwares.
Excuse me,
Yes,
but when does class end?
the class ends at 5:30. Yeah, so as you might recall, as I talked about before, one place where you can get the CAD model for this kind of hardware, if you do want to include the hardware in your assembly, like you want to put the bolts in or the various screws, fittings, and nuts, then you can download the appropriate hardware from McMaster. And I think recently, about a month ago, McMaster started to require you to log in to use the CAD models, which is a bit unfortunate in my opinion. For example, if I wanted to get item number 11, which is this nut here, quarter 28 steel machine screw nut, I'll just go like hex nuts, anyone. I need a quarter 28, this one here, and oh, they made it. Okay, so now we actually can download things again. So there was a temporary change, it seems. So to complete my assembly, if I wanted to be very thorough, I could go find my hardware and import it. Now you can see the nut, the specific nut that was used to fasten things here. So what was that? Item number 11. That one goes here. And I can also add this to my assembly. So insert. And what I can do is, I guess I'm not going to demonstrate putting in all of the hardware. So if you did put in all the hardware, you'd probably do this a bit differently, but what I can do is place the nut where it belongs. So you can imagine if I repeated this for all of the additional hardware that's in this assembly, bill of materials, that I would have a slightly more accurate and realistic model where you can actually see the relationship between these, where these holes are placed and what allows them to move on each other. But for the time being, like this is completely functional model. I may have put this bolt in the wrong place or this nut in the wrong place. Let me see. Oh, it goes on the flywheel, my bad. So yeah, on this side, I can do something like this. All right, so if there are no questions about this project, then we've now officially finished the air engine project. So congratulations. By doing this, you've the main outcomes of what you've gained from doing this is you've modeled a number of parts by looking at the drawing. So as you remember, for every single one of these parts during the corresponding class, you had to learn how to read and how to create a model by looking at the drawings. So every week, like you did one of the homeworks, we worked our way up from like a relatively simple part to a relatively more complex part like the flywheel. And after that, we did an assembly, which is a bit more complicated than the ones that we've been doing before. We have kind of different kinds of motion. We have relations between, for example, the flywheel and the crank wheel, or parts with more than one mate on them. So hopefully that was helpful to you. Okay, so now this is the second to last week of the class. Next week is our last class. And this week, what we'll be starting is our third project, which is designing a keychain. I'm not sure if this one is true for this session, since I'm not related to like the actual AOE center. So this is question mark. You can ask Missy about it if you are curious, but the idea is to design like a simple keychain or like a keychain attachment. So on your keychain, you might put something decorative that helps you like hold on to your keys. The only restriction that we'll place on this project is that you limit the bounding box to 3 by 3 inches by ½ an inch. And the reason for that is firstly that anything larger would probably be an inconvenient keychain. And second is that if it is possible for you to receive these 3D printed, then that is the size that they want you to have. So you can go ahead and create a new document. This is for your keychains. And I'll show you a few tools in Onshape that you can use for this project that you might not know about already. So to start out with, this project is a bit of a different flavor than the Air Engine project that we've been doing up to now. The Air Engine was more of a technical kind of engineering type of CAD project where everything needed to be accurate, a certain size, with certain position of all these holes and features. On the other hand, a keychain is pretty non-functional. It's almost completely decorative. So the design of the part is kind of very much a matter of your own preferences. So for example, one classic idea, I suppose, is perhaps a keychain with your name on it. Okay. So in the sketch features, you may have noticed this before, is the text tool. And this allows you to create text in a number of pre-specified fonts from Onshape and create that as a sketch feature. So if you want to write words, there's no need for you to try to recreate a font using lines and arcs and splines. What you can do is just use the text tool, drag out a box, and then I can spell something like that. And what you'll see is that if I extrude this, this is what I get. If you need to control the size of how big the text is, what you need to do is limit the size of the height of that box that you draw using the text tool. So for example, let's say this is not the size of your actual keychain, but let's say that I'm working with a block that's 3 by 6 inches long. And if I want to write my name here, I need to make sure my text box, first of all, that it does not exceed this, but also that I have enough length for the entire word to fit. So for example, a short word can probably fit here. But you can see this word is actually too long. So in order to actually fit the entire word, I might need to make it a bit smaller when I first draw it. And you can see now that it fits. Unfortunately, with Onshape, it doesn't allow you to rescale the letters once they're in position, I believe. I wonder actually if I can. Okay, you can do this actually. So you can control the size of your letters just by dimensioning this box. And otherwise, you can work with it like any other sketch feature, like a line or yeah, like a line or anything else. Another thing that you should note when you use letters is that a lot of the time you can't create a solid object that is cut entirely with the letters. So for example, if I want my name to appear properly, like this, then what I actually get is a number of different parts. So you can see that when I created this extrusion, it actually created 4 different parts. We have this part here, this one here, this one here, and this one here. And in my left, underneath my feature tree, I can see that I actually created these 4 different parts. So when you're creating a part in real life, you can't actually do this. If you try to 3D print this, you'll just be left with, for example, you'll have this piece, then you'll have also this piece, and also this piece, and also this piece, which is not really what you intended. So if you want to create something like a block with a word on it, and the word has letters like G or E that have holes inside of them, what you will need to do is to slightly modify the letters. For example, for this G, I can add I'm not sure if this works, but oh, whoops. Okay. So you may need to modify the letters in any case so that they have a connection between the parts here. So you can also do it after you create your first extrusion. For example, I can do something like this, and then I can extrude another shape that connects from here to here. And then I can extrude this shape in the middle, and that will connect the blocks together. But another way that you can get around this without doing that is to not cut the letters all the way through the block. So if you have your letters, I'll just demonstrate with the N. And what you can then have is kind of a shallow cut like this. So that is one thing that you can do if you want to have text in your design. That is one thing you can do. Another thing that's popular is to kind of create your own shapes using this tool, which is called spline. So spline is kind of a curve, but it's not necessarily a circular curve. So you can have multiple different radii of curvature. And so simplest spline just has two endpoints and these two things which are called spline guides or spline. I'm not sure what they're called actually, but what they allow you to do is you can drag them and they indicate the tangent direction at the point where the spline ends. So here you can see that I can create some curves which are not circular with the adjustment of these two spline guides. And so in order to fully constrain a spline, you need to fully define 4 points, the endpoints and the two guide position points. So you'll see that like I can specify dimensions like this. For a point, all you need to specify is its position and it will be fully constrained. So at most, you'll need 8 different dimensions in order to fully dimension a spline. And so you can imagine for that reason that splines are kind of a bit complicated. A lot of the time we don't use these to design like mechanical things, but it's often okay to use for if you're just like trying to create a certain shape. Another key thing is that you can use more than one spline point in a single spline. So this one is a 3-point spline. So now I have this intermediate point, which I can control. And I also have these guides that I can control. So as I increase the number of spline points, the actual geometry that I can achieve becomes a lot more complex. And I can do some interesting things that I can't do with only 2 points, but I need this 3rd point to do. And likewise, I can do this as many times as I want. I can have as complicated a spline as I want in order to create any kind of shape that I want, kind of like I'm drawing a shape with a pen. But I will warn you that the more spline points you have in general, you can consider that most of the time you don't need this many spline points, right? You can achieve a lot with just lines and circular arcs, so don't feel the need to use these splines unnecessarily, but it is a tool that exists and can help you create a design if you want some kind of fluid shape that you can't easily express with just lines and arcs. And finally, some other things to think about as you work on this project. There are some limitations with what 3D printers can do. And one of those things is the minimum thickness of a part. So if I design something, let's say a circle and another circle, let's say I'm trying to create like a ring, some shape like this. The problem is that if I design this to be too small, then it might not be possible for my 3D printer to actually create this because like the wall is too thin. So either I'll attempt to print it and then it'll be too thin and too weak and it'll break, or it'll be so thin that it's not physically possible for the nozzle of the printing head to actually create this kind of thin wall. So you can imagine if I'm trying to make a shape like this, this might not necessarily be a printable shape. So there's a few rules of thumb. And in general, for the 3D printer that you're using, whichever one it is, if you have access to one, you probably know what it's called. So you can just search the specifications for your 3D printing. In my case, I don't have any specific one that I'm working with, but you can just look up things. If you ever have any questions about like, what can I do with a 3D printer or what can I not do with a 3D printer, you can generally look it up, and 3D printing has been around for a very long time and accessible to hobbyists. So many resources are present which you can rely on. So I think maybe something like 1 millimeter, something like 1 or 2 millimeters is probably a safe bet for the minimum sized feature that you can safely create. So this one is a bit of a contrived example, but you can also imagine, let's say I'm trying to create something and I want to make a shape like this. Um, and okay, well, this example is not the best, but you can imagine if I have like a really thin pin or a really thin wall that exists. In those cases, you might not be able to print these things. Other things to watch out for, as you design things, you'll quickly learn that you actually design a lot of really thin or small geometries without even realizing it. So, for example, a lot of keychains are going to have like a hole for your keychain part to go into, like the actual chain link to go into. So for example, you might design something like a rectangle, and then at the end of it, you might have something like this. So when you do these things, just make sure, like for example here, make sure this wall is thick enough between here and here.
Can you show me the sketch? Because I wasn't finished with the sketch when you came here.
For this?
I mean, can you show me the sketch again?
For this?
Yeah.
Okay, that was a really fast and dirty sketch, but basically you have two circles. You kind of just position this somewhere and you can extrude them.
So how did I do it? Like, but I can't move it. How do you move it?
Whenever you have a question like that, the best thing to do is just like delete it and start over, because you probably created some kind of constraint automatically, like Onshape guessed that you needed this constraint when you really didn't. And then that kind of messed you up later on. So if you're ever having a problem that seems kind of simple, like needing to move something, but it's stuck, it's usually just a matter of it having some extra constraints that shouldn't be there. So if you like delete it, retry it, it should probably work.
I'm gonna try again.
Yeah, that's a good idea. So next week, I'll talk a bit more about other considerations that exist in terms of 3D printing. And I'll probably do a demonstration of how you can take some kind of image from like any kind of image or picture, and you can recreate that in CAD by tracing over the image with splines. So it's a fun technique, not that useful, but it's a cool way to get a shape into your model without too much effort. And I see there's a question about CAD 3. That is a class that exists and I have taught, but I'm not really sure when or if that will be offered, just because I'm probably the one who has to teach that, but I don't think I will. If it is offered, you'll know, but it might not happen, at least very soon. So yeah. In any case, it's just about 5:30, so if you have any questions about this or any of the things that we've talked about, feel free to ask me. Seems like there's an event happening downstairs and you might be able to hear that. Don't worry.